Thanks for having me. My name is Danny Ryan, work at the EF. Do some research, different protocol design, and like a lot of stuff on just shipping mainnet. So we'll take a quick look at L1 security. This is, I think, very high level. I think it's probably interesting if you don't take a look at this stuff often or in the application layer. Kind of go through some of the various domains, how they relate, and some of the issues that we see and think about in L1 security land. Just a quick tip, avoid complexity. Complexity is evil. I think almost all of the bugs that we've seen either on mainnet testnets or caught before are often related to complexity and not related to some attacker knocking on the door. Every once in a while, an attacker does knock on the door, but usually complexity is the enemy. 10,000-foot view, although that's very American, so it's a 3,048-meter view. So the things that we tend to look at L1 security is consensus. So essentially, can we provide some sort of agreement mechanism on this network? Mechanism design is more of the higher level. Okay, we have consensus, but how do we incentivize it? What type of gadgets do we have in it, and what type of features in there? Concrete specifications with respect to those things. Then we have to figure out how to correctly implement these things with respect to the specification. Then we have to actually like instantiate this in the real world. That's where most of the problems are. And then we need to know what the hell is going on with it, and if something goes wrong, figure out how to recover. So consensus, trees, chains, actions, and decisions. Essentially, consensus usually is the summation of user action. In a blockchain, it looks something like a tree, but usually we're trying to pick a single chain of history through it. So consensus is, given all of these messages, let's find a canonical one to agree upon. And sometimes we disagree. Sometimes we switch views and have different changes in consensus. Safety, at least from the consensus of Ethereum, has proven to be easy. It's not terribly difficult to have unions of people agreeing on chains and figure out finality, but it's certainly catastrophic if and when it's broken. That's when the slashing and other sort of catastrophic things can happen. Liveness and view splits and trying to figure out how to confirm things in front of finality has proven to be much more difficult in Ethereum. And it's almost entirely because of decisions that we made due to complexity. So essentially, in traditional consensus, we have quorums. If quorums agree on things, we finalize things. We need to have a quorum to kind of move on. In Ethereum, we have this thing called the available chain, where we try to build blocks ahead of the full quorum, and in doing so, end up with quite a resilient property. A lot of the nodes in the network can go down, a lot of validators can potentially disagree, and we can still make progress in some sense. But in trying to create this Frankenstein of a monster, these are where the issues lie. There's supposed to be another emoji right here. One of the big things that has been a problem is view splits. Essentially, I see this chain in the middle as canonical, and you see one of these other chains as canonical. Because of the timing of messages, because of the particulars of my node in relation to yours. And these have been kind of the pain of Ethereum consensus since phase 0 launched. Once we get kind of the cradle of consensus and we get kind of the theoretical components here, then we have to instantiate it. We have to, like, what is the game, who are the participants, how it's played, and how it's incentivized, right? So traditionally, consensus doesn't necessarily answer a lot of those questions. In a blockchain, we have to instantiate these things. So at a high level, what is the game around constructing the chain? What are the sub-games within? Like, what can I put in a block? What are some of these other things like base fee in relation to it? What are my payouts? What other messages can I include? All of the gadgets and features, including even the EVM, that interacts. All these things interact. Nothing's really in isolation. And constructing something like Bitcoin would probably be much easier because we don't have this arbitrary interaction with the programmable layer, the smart contract layer. Anything can be programmed into this into the cradle of consensus with the EVM. And so we get things like EGLs, like people trying to have a gas voting token. We get on-chain bribes. We get things like Lido, where you're layering like arbitrary kind of things and incentives into the consensus itself. And so I think there's probably reasonable equilibriums in mechanism design in Ethereum and these types of systems, but you never know what's going to be thrown at you next. And then there's a handful of things. I think the easy assumption is you have some set of actors are honest and some set are dishonest. A harder way to kind of construct and the assumptions about the environment is a subset of actors to some percentage will be rational. So say, we're willing to say like groups of actors up to like 12%, 15% of the network are rational, but they're not colluding across these thresholds. And then the hardest thing is if people are willing to collude beyond these like these subsets such that you're over certain thresholds like 30, 60, 50%, whatever. These systems do break over certain thresholds, so at a certain point, if people collude, it's going down. Often what we see, the issues in these mechanism design is not accounting for some player or some incentive when you're constructing the game. So for example, most of the theory around launching the beacon chain around target stake rates had to do with issuance. And some understanding of marginal fees on top of issuance. Whereas in that time span between developing the beacon chain, launching the beacon chain, and instantiating the reality, MEV became a thing, right? So now there's a new player, there's a new incentive, and target stake rates, so assuming 30% or so of the network is going to be staked, goes out the window because we now have like a new incentive and a new player in the game. Next up is you have the mechanisms, you have these pieces going to fit together, you have to write a specification. Turns out this is non-trivial to translate theory and mechanisms into like cohesive, correct, and actionable specification. There's a number of ways to do this if you ever read a specification. First, you can just have lots of words. There are some merits to just writing down the damn thing. You can also have pseudocode, which is the path that we went for the consensus layer for a bit. Eventually, that transitioned into sprawling spaghetti of Python code. We were writing pseudocode that looked a lot like Python, so then we thought, maybe we'll write some Python. So now the consensus layer does have this executable spec. It's not formal in the sense of like formally verified, formal type code, but it is generally complete. It is executable, and it does run. And so now we have this executable spec that has its warts, but has actually been quite nice because as we write down the behavior of the core components of the specification, we also do get to run it, and we can generate tests and other things off of it. Issues in specification, they're almost always interactions of components with each other. Usually, like say you're specifying an exit, it's like, how do you exit the beacon chain? You sign a message, you verify the message, you change a few state variables about a validator. But the problem is when these components interact with other things to produce kind of like edge cases in relatively complex ways. So maybe that validator has some balance below threshold, maybe that validator's already been slashed, maybe all sorts of other things. And so try to isolate these things. It's not always possible. Correctness of implementation. This is actually where the hard work starts. You have a specification, and now you're trying to write software to actually implement the specification. First of all, the spec needs to be implementable. Then you get all the kind of like normal things. You get testing, formal verification, fuzzing, audits, bounties. There's no silver bullet, but each of these things kind of plays a role. A nice thing that we have in Ethereum client L1 architecture is that we actually have multiple implementations. And I would say that a very large amount of the bugs that we catch before going to mainnet is because we do have multiple implementations. It's hard to imagine developing in a world where we only had one implementation, where we had a spec and we had an implementation, because frequently you have the spec, you write the software likely looks like the spec but doesn't catch all the edge cases. The software goes to mainnet. The software then kind of is once it hits an edge case, kind of is just defined by itself. Whereas with multi-implementation, we catch a lot of these kind of edge cases early by vetting the software against each other in kind of a semi-production manner. When there's an issue with respect to implementation, with respect to kind of the core specification, usually manifests as a consensus split, usually manifests as us, my client disagreeing with your client, in usually kind of an irrecoverable way. Maybe like my balance is one off of yours. Now we can no longer communicate and agree on the same chains. And furthermore, these things are often caught by testing before you actually get to a client actually being in the wild. Except that caches are evil, and these things become very stateful. So maybe in the testing environment, maybe in like the instantiation of given this state, given this block, what is the result? It's very correct. But in the wild, it turns out that you have all sorts of caches, you have pre-computes, you have all these other things where the assumption of where this code is running and in relation to the state that it's accessing, though the assumption and relationship between those two things can be like very off. And almost always, especially in the consensus layer, when we've seen bugs in relation to this, it's not because the simple logic of executing the specification was incorrect. It was the relationship of the execution of that specification to the underlying assumptions around state and other things going on. So like, I guess, for example, if I'm executing, I think I'm grabbing a validator, I think I'm manipulating the validator and reading certain things about it in relation to the state that is supposed to be the pre-state, but instead my cache did some optimization and that validator is in relation to the pre-state from the previous block, that kind of stuff. And that's where a lot of the complexity and issues arise here. And then this is actually where the hard work happens. So like the blockchain, the blocks, the virtual machine, the consensus, it's not necessarily the hardest part to get right. It's really these things have to run on computers, talk to the internet, manage keys, and do all sorts of like complicated things once you get that core correct. And that's where even more of the issues actually arise. This is the really hard work, not just the hard work. And when I say the real world, I mean the P2P. I mean my node, finding friends on the internet, talking to them, handshaking, listening to messages from them, optimizations, pre-computes, and caches, databases, and getting cryptography correct. And some of the issues that we see here, I think easily, I don't know the number, but a lot of the issues that we've seen in bugs that usually don't make it to be exploited are DOSes on the P2P. So given I'm talking to random people on the internet, I at least want to, if you send me a message, I don't want to do more work than the message that you sent. So I don't want an asymmetric load with respect to your message. But frequently, you might send a message and there's a bug where the message was this size, but it makes me all of a sudden fill a memory buffer of that size. So we have DOSes, crashes, partitions, DOS with respect to compute. So one of the big issues that we saw on mainnet, I guess it was earlier this year, was in relation to Prism getting weird messages, pointing to old messages and doing, like not having the proper pre-compute or anti-DOS measures such that I get that message and all of a sudden I have to like pull out something from a database and do a lot of execution on it. Remote code execution is like the thing of nightmares. Fortunately, we have primarily memory-safe languages these days, so I don't know if we've seen in RCE even I mean, we definitely haven't seen one in mainnet, but I don't think we've even seen one like privately that we've had to fix. Lost keys, phishing, supply chain issues, dependency poisoning, all sorts of problems with the social layer, and then even potentially legal jurisdictional issues. Monitoring. I think back to the launch of Phase 0 and the amount of monitoring we had. Certainly had logs, great. Certainly had some pretty cool Grafana dashboards, but I think we were woefully unprepared in terms of the amount of monitoring we had. It's been really fun working with ETH-Panda Ops. They've done a really, really excellent job fleshing out monitoring, running test nets, and all that kind of stuff in the past year and a half. Finally, we think about recoverability, but we can talk about that later. Real quick, the relationship to the application layer security. L1 provides a consensus and isolates applications from most of the real world concerns. You don't think about reorgs, you don't think about P2P, you don't think about all these types of things, but kind of at a distinct loss of recoverability. You don't get a native way to jump in, fix your software, and all that kind of stuff. But maybe that's the point. Anyway, thank you.